Welcome to The Explainer. Today, we're unpacking an industrial wager so incredibly massive, it could literally reshape the entire global semiconductor industry, or, it could end up as one of the most expensive miscalculations in modern history. We're looking at Elon Musk's absolutely staggering $122 billion gamble to build TerraFab. This is meant to be the world's most advanced, most power-hungry chip factory. The ultimate goal? To solve a massive existential threat currently facing Tesla, SpaceX, and xAI.
Okay, let's just jump right in and look at this wildly massive number, 1 terawatt. That is TerraFab's potential future power draw, if the leaked scale of this project actually holds up. Just to put that into perspective for you, the entire state of Texas, which, remember, operates one of the largest power grids in America, draws around 85 gigawatts at its absolute peak summer demand. So Musk isn't just building a factory here. He is literally attempting to concentrate a very meaningful slice of the entire United States grid capacity onto one single site. It's wild. So here's how we're going to break this down today. First, we'll look at the $122 billion gamble itself, followed by the silicon bottleneck that's really forcing Musk's hand here. Then we'll cover the Intel talent gambit, the two completely different worlds they're building chips for, the unbending limits of physics, and finally, we'll ask, is this going to be a massive triumph or a massive miscalculation? Let's get into it.
All right, starting with part 1, the $122 billion gamble. Picture this. You're in rural Grimes County, Texas. Out there on an empty patch of acreage roughly the size of 1,700 football fields, Tesla is trying to concentrate an unthinkable share of the world's computing power. And why? Well, because this whole TerraFab project is really about survival. It's not just ambition for the sake of ambition. Musk reportedly spends over 60 hours a week focused squarely on just two things, the Optimus humanoid robot and the robotaxi driverless fleet. And by his own account, both of these are basically ready to scale up. It's not the design holding them back. It's not the manufacturing lines. The single glaring bottleneck right now is a severe, widening lack of chips.
Which brings us to section 2, the silicon bottleneck and the existential threat it poses.
See, physical robotics and AI have fundamentally changed how we need to think about computing. A modern Tesla isn't just a car anymore, it's a supercomputer that happens to read the road. To power this kind of future, you really have to look at this totally terrifying reality when it comes to global chip supply. If you take the entire semiconductor industry as it stands today, we're talking heavyweights like TSMC, NVIDIA, Samsung, all of them, they could currently satisfy only about 2% of what Tesla, SpaceX, and xAI are eventually going to need combined. 2%. That 98% structural gap, that is exactly what this $122 billion is trying to fill. We're not talking about a little supply chain hiccup here. We are talking about a completely different scale of demand.
Now, to really wrap your head around why they need so much computing power, you have to consider what's called the 3D problem. Think about a self-driving car. It basically only has to understand a two-dimensional problem, right? The road ahead of it. But a humanoid robot like Optimus, that thing has to balance on two legs, coordinate dozens of joints all at the same time, and react instantly to a totally chaotic, ever-changing 3D environment. That kind of computational load instantly dwarfs what any smartphone or laptop has ever required. It demands endless frontier AI training.
Moving on to section 3, the Intel talent gambit, and how Tesla plans to skip the queue.
You're probably wondering, how on earth does a car company with zero semiconductor manufacturing experience actually run a fab? Well, their strategy is essentially to just buy decades of discipline in one single massive move. Instead of waiting in the back of the line at TSMC's delayed Arizona plant, which, by the way, is expected to handle older tech anyway, Tesla decided to just opt out and skip the queue entirely. Back in April, Intel officially joined the TerraFab project, and Tesla poached Gary Zheng. Zheng is a 17-year Intel veteran who actually ran their most advanced manufacturing operations. Tesla is heavily leaning on him to help them leapfrog straight to Intel's bleeding-edge 14A or 2-nanometer process by 2027. But here is the absolutely crucial point. Inside a 2-nanometer clean room, you simply cannot use the old startup mantra of move fast and break things. A modern fab floor requires thousands of highly specialized skills stacked perfectly together. The vibration control has to be so insanely precise that a single truck driving past the building outside can completely throw off a production line. The air filtration has to be so pristine that one single stray particle of dust can literally burn tens of millions of dollars in ruined wafers overnight. No pressure, right?
Tesla is essentially betting that throwing enough talent at this will transplant all that institutional muscle memory fast enough to actually matter.
All right, Section 4, two chips, two worlds. This is a massive dual-front war. With TerraFab, Tesla is basically fighting a massive dual-front war for two incredibly hostile battlefields. On one hand, you have the AI-5 chip, which is supposed to begin its initial ramp-up this year. This chip is destined for Earth. For those Tesla vehicles and Optimus robots we talked about, its entire engineering goal is speed and adaptability, making split-second decisions at chaotic city crosswalks. But on the totally opposite side, you have the D3 chip. This one is destined for orbit, to turn Starlink into a massive orbiting data center known as Sirius. The D3 isn't about adaptability at all. Its core goal is pure, stubborn endurance in the vacuum of space. And building computer chips for orbit is notoriously difficult, mostly because you don't have Earth's atmospheric shield to protect you. Engineers have to design against something called a single event upset, or SEU. This is a very real, very scary failure mode where a high-energy cosmic particle literally passes straight through a chip, and it flips a memory bit from a 0 to a 1. And it doesn't just cause a little glitch that you can quickly reboot, it can silently corrupt the exact system that's keeping the spacecraft stable. Now, what's really interesting about this is the sheer proposed scale of producing these chips. It's just staggering. TerraFab is reportedly targeting an initial capacity of 100,000 wafers every single month, eventually wanting to scale up to 1 million wafers a month. Just to give you some context on that, 1 million wafers a month would equal roughly 70% of TSMC's entire current global output. TSMC achieved their massive output through over 3 decades of compounding, hard-earned experience. Musk is aiming for those same numbers starting from basically empty acreage in Texas. Which brings us to Section 5, the limits of physics. These are the constraints of reality. Talk to any industry veteran and they will tell you straight up that $1,220 billion still does not buy you a workaround for the laws of physics. Let's look at 3 major constraints that money just cannot solve. First, you've got extreme ultraviolet lithography machines. These are built by literally one single Dutch company, ASML. They cost up to $400 million a pop, they only make a few dozen of them a year, and you absolutely cannot just skip the queue to get one. Second, semiconductor manufacturing requires extraordinary volumes of ultra-purified water. Replicating this kind of massive scale in a drought-prone state like Texas, that could require up to 200,000 tons of water daily. You basically need a dedicated river just for the factory. And third, there is the terrifying issue of silane gas. Silane gas is a core chemical used to deposit the silicon layers onto these wafers, and it is highly, highly pyrophoric. What that means is it ignites spontaneously the very second it touches ordinary air. When you're trying to concentrate the sheer volume of silane required for a facility of this unbelievable size into one single location, you are dealing with a severe industrial hazard. A leak is never just a minor incident here. Containing it safely is an issue of basic chemistry that very harshly punishes small mistakes, and it really doesn't care how much venture capital backing you have. Finally, Section 6, triumph or miscalculation, weighing the massive ambition. Look, on one hand, Musk's most committed supporters will rightly point out his track record. Experts once said Tesla had no business trying to make mass-market EVs, or building their own complex battery supply chain, or, landing reusable rockets backwards on ocean platforms. But he found a way through. But on the other hand, a leading-edge chip fab is an atomic-scale precision problem. A lot of Wall Street analysts and veteran engineers argue that this time, the wall he's hitting isn't made of public doubt or red tape. It's made of unbending water tables, highly dangerous chemical limits, and global supply chains for machines that literally only one company on Earth can build. So we're going to leave you with this final thought to ponder today. Can sheer willpower and $122 billion actually compress decades of semiconductor muscle memory into just a few short years? Is TerraFab about to completely redefine what one single company can build? Or is it quietly shaping up to be the absolute most expensive miscalculation we have ever seen? The laws of physics are officially on the clock. Thanks for watching The Explainer, and keep questioning the world around you.